So since we didn't talk much about exascale, or exaflop, or exabyte, what we wanted to do in the next hour is to do a panel and to cover anything that's interesting under the theme of the road to exascale, which pretty much covers everything in the HPC space. So I'm going to do some fire talks with Addison. We don't need to have them answer if we don't want to, right? We control it.
Okay.
So I've organized a set of questions myself, but the first priority is question from you guys, right? So if you have questions to ask the great panel, which includes, depends where I start, but Mark Seager from Intel, Ellen Poston from Xyratex, Bill Boas from Cray, Panda from Ohio State University, and Michael Kagan from Mellanox. So you can address them, you can address any one of them or all of them and ask questions. I'm going to start with my own, but whenever you have something that you want to ask or bring up, or bring your own idea, please do. So I can go through mine, and if you want to jump in a question from your own, feel free.
Okay.
Thanks. So, first question that I wanted to ask the panel is, worldwide funding are being placed as part of developing technologies and solutions toward the exascale. There's multiple RFPs out there to build systems in the next 2 years, the next 4 years or 3 years, trying to bridge the gap between what we have today and what is required for exaflop or exascale. In your mind, and it's a question for the entire panel here, in your mind, what are the major gaps that you believe that funding should address now? What are the more critical items that funding should go to?
Yeah, so by far the biggest challenge is the power, the flops per watt, especially delivered flops per watt, to applications. And that is the unfortunate thing about that news is that that's a long lead time item to fix. There's, lots of research that needs to be done in architecture and different ways of building circuits and resiliency, all that kind of stuff. And that I think is the linchpin, to get to exascale. And the other stuff, at least on the hardware side, ends up relating to how we try to solve that problem. And if we go to near threshold voltage circuits and those kinds of things, the resiliency problem gets way harder, and there's a lot more basic research that needs to be done. If we just do the brute force thing, like we are today, we're going to miss the exascale power targets substantially. So, you can pay me now and do the research, or you can pay the utilities later with the power bill. And then the bills are about the same, actually. It's kind of fun.
And you'd rather they pay you?
I think, for the betterment of mankind, we burn a lot less fossil fuel, and HPC would contribute less to global warming if we reduce power.
So I'm an I/O guy, and I think the next exascale problem past power is I can shout.
It probably just have to be closer to you. Yeah.
So, like I said, I'm an I/O guy, and I think the next problem in exascale is I/O, and it's both a software and a hardware problem. I/O hardware has been lacking compute hardware for decades, and it's only getting worse. We've done unimaginable things to improve the I/O rates and the storage capacities, but we're not solving the fundamental problems of rotating mechanical storage. The next problem beyond that is the software stack is going to have to radically change to adopt to these new hardware paradigms.
My views are quite close to Alex, but I'd like to ask Mark. you define Exascale as exaflops. If it was exa something else, would the problem be the same?
Well, I didn't define it as exaflops. I think it's exaflops and exabytes, and storage, memory, and long-term non-volatile storage being primary on the exabyte side. Big data requirements coming out of science and also commerce, websites and mobile and all that stuff are driving storage really hard, and there's a lot of synergy there to be had. So I think although we say exaflops, that my view of exascale is exabytes and exaflops.
So do we need a radical change in architectures to move the data nearer the processors?
Yeah, absolutely, absolutely.
I'll keep this one.
Hello. So I agree with Mark about the power issue, but the power issue, as Mark indicated, it depends on it's like you need to resolve it from bottom up, from the architecture and logic, and that will take a lot of time. So rather I think that with the current technology also an intermediate goal will be how to design the software stacks to conserve more power. If we can do that at least with the available technology or near available technology, then those things can be used in a longer term when the better architecture comes, and then they can be married together for the Exascale system. So in that context, I think the programming models, the software stack, those I feel that more important in the next 5 to 8 years.
Okay, so after power, storage, and application were covered, I think there's two more things that needs to be taken care of. One is the physical layer. We are going to approach, terabit per second or maybe even higher link speed required. So, and I don't think we have a technology today that can, that can be working at these rates in the near future. There are some developments of silicon photonics and the like, but it is still, I don't see how we can get to these rates yet. The second thing is resiliency of the big system. Today there is quite a lot of developments in the enterprise and Web 2.0 space on using virtual machines for managing the resources. And I think it would be really beneficial for very large scale machines to look at these technologies and to deploy them, rather instead of putting many virtual machines on one physical node, maybe having the entire application running on top of virtual machine that's basically spanning across multiple, thousands of physical nodes.
Everyone started from whether or not they agreed with Mark. I'm going to conditionally agree with Mark, which is to say that I conditionally disagree with Mark, right? That in your own speech, you talked about exascale as really you're talking about the whole exa era. And if what you're talking about is getting 1, 2, 3 research applications to run at an exaflop on the first exaflop machine, then I agree with you conditionally that power is the hardest thing. If you're talking about the era of applications running efficiently at exascale, I think it's software by a mile is the hardest thing. And that's where DK went with his answer. And when we talk to end users about what's it going to take to run even efficiently at petascale, let alone 1,000 times more than that at exascale, software is all they can think about. Predominantly application software, but I think that's the end user construct that they think of, and the end user application software is going to be reliant on middleware that can manage it. So I think it's hard to talk about the end user application software without the system software and middleware layer that enables it.
No, in taking this one, I completely agree with you, and it's kind of jumping to my last question at the hand. We'll go back to the previous questions after. But one of the things that I agree with you, one of the things is the software side. And I think there is not enough education of HPC programming levels on university base, right? So I think what DK is doing in Ohio State University is a great thing, but I don't think that there is enough in other universities. Right. And there is not enough to bring the new generations of programmers that can leverage from the skill. You know, a few things that we're doing from the concept perspective is that we did a pilot end of last year where we did an RDMA competition in China. And we invited multiple universities to go and do some programming on RDMA and see what they can do with it. This is something we'll try to do more because we think that we need to bring more and more HPC knowledge into the universities, into the young students. But you know, the question is, are we doing enough there? Or maybe some of the funding needs to go to that area.
You raise an excellent point because, you know, we cheated. We only answered half of your question by talking about what the biggest problem was. The other half of your question was, where do we need an investment? And if you apply that to the software aspect, it's actually difficult to figure out what you mean by investing in software for this, because it's actually a pet peeve of mine when government of this country or any others starts investing in, we're going to create open source software that scales, and spend all this government money on it and have it undercut commercially available software that's already in the market, right? You know, but then, you know, the ISV can't find the business case for investing it on their own. So finding a business case worthy investment model from government into software that doesn't undercut the market is actually pretty tricky.
I agree. So you know, DK is for you. In your eyes, you know, I think you're doing a great job within Ohio State of bringing that. But you think there is enough in other universities?
I mean, so I think we started like in the very early days, but I think gradually I see some other universities are picking up. Again, it is not very difficult. It is just a question of like getting exposed to the students in the right way, saying you need to learn some basic RDMA programming, and in these are the benefits. I think China, as you said, there is a lot of interest there, and I think in US, some universities I have seen, Europe also is catching up at several places. So gradually, like the low-level RDMA level-based programming is catching up, but it has not. It'll be good to accelerate that, but whether to do it through the funding model or a business model, I don't have that answer.
I'll take off my Xyratex hat and put on my former NASA hat and say that government funding's been the only thing that's pushed HPC forward in 30 years that I've been involved in it. And I think there is not a commercial case to be made for the innovations that you're speaking of to go to Exascale. There's only going to be maybe 5 Exascale machines built in the next, say, 5 years?
Yeah.
Well, I appreciate that viewpoint.
Yeah. So, you know, on the application side, I think we need to talk about the democratization of HPC. This is actually a big theme in India's HPC program. You know, they're not going for the biggest, they're going for the broadest, right? Exposure of HPC, they do call it the democratization of HPC. And not only is application development important in that regime, but the level of sophistication that's required to use that software also needs to be addressed. And we, at Intel, Stephen Weed in particular, has identified that as one of the inhibitors to the missing middle piece of the HPC market. It's dominated by the high end, and there's lots of the volume space, but that departmental server, up to $1 million range has kind of disappeared, and the apps are the exact reason for that. So I disagree that there's not more economic drivers than there has been in the last 30 years. The predictive simulation capability of applications today are revolutionizing the way that people are thinking about manufacturing things. The whole maker market, the whole maker movement, is a perfect example of that. Where you can virtually design things and then punch a button and do a 3D printing of objects that are quite phenomenal. That has the potential to radically change the way that we engineer and manufacture and design things worldwide, and basic simulation capability is a huge driver for that maker movement. So I think there's sightings of economic indicators of a potential phase transition.
We always said that cutting edge turned into leading edge turned into cutting edge turned into mainstream, and that's been true in computing since its invention.
Maybe I'll ask a follow-on question for Mark there. So, developmental servers, we can build those now, right? Those can be purchased. That would necessarily, maker movement would necessarily drive an exascale system. Like, I'm not going to design an additive device that I can additive code machine to build at home. And that'll be an exascale machine to do the line element analysis of that.
Right.
What is the killer app for exascale? I'm impressed when I can see 2 million processes running currently. So that's an application for ENS application. Cool. But for real geometries, real problems of interest, what application do we know of that actually will do that exercise an I'll say hexaflop machine for now or at some point in the future? We're going to need the microphone to the audience if they're going to ask questions, or they're not going to hear it on the video. That's right. If you got a question, that was a long question to repeat. You can repeat it.
So the question was, what's the killer app for Exascale? And I think accurate weather prediction, climate prediction, short term. We're worried about a drought here in California. How long is that drought going to last? That's a question that you need a global climate code with regional capabilities, weather prediction capabilities. Aircraft modeling and design, engine modeling and design. The bioengineering stuff that's going on, both in terms of genomics, but also in terms of prosthetic devices and those kinds of things. If you just keep looking where predictive simulation can, inform science in a breathtakingly accurate way that we couldn't do before with Exascale, those are the Exascale killer applications. Now, a lot of those applications are nascent or are in the process of being developed, waiting for the machine, and I agree with Addison's point earlier that those development activities need to have a clear business case, and they need to have government-sponsored funding to help make it happen, because that's part of the role of government here is to create that new infrastructure, application infrastructure. It's a very interesting debate about what the right balance is between applications and the infrastructure for the system, both hardware and software. And my view is that the application investment needs to be larger than the investment we make in the system development themselves. To do this democratization at the bottom but also to create new leading edge capabilities that become cutting edge later.
Where does the panel see the real big innovators like Google and Apple in exascale computing? Have they got a visible role? Is what Google is building? Let's repeat the question.
So the question is, where's Google and Apple with respect to Exascale? And I would say, Microsoft, the telcos, Google, Apple with iTunes and all that stuff, Amazon, they're all playing at the leading edge of scale-out infrastructure, which rivals what we need to do for Exascale HPC. The major difference is they're mostly a throughput workload, a workload that's inherently resilient. Ours has a tightly coupled asynchronous communicate model that makes it less resilient. So we have a different set of problems, but in terms of base technology, those guys have a lot of the same problems that we have. And I think, it used to, to your point, it used to be, in the killer micro revolution and going from proprietary operating systems to Unix, and then from Unix to Linux, the thing that was driving it was desktops, right, and laptops after that, and now it's mobile that's driving it. So in terms of the real economic innovation engines that we're going to have to live off of for HPC, it's phones and tablets, believe it or not.
And Mark just took my entire answer. The real driver that they add to the market is the commodity that they bring, which is they commoditize everything, and we have to build our systems out of the same elements that they build their systems.
It's not entirely true that they're commoditizing everything. I mean,
Except
they're bringing
for
things
few
like
things.
Ultram Alpha to Siri and to the world. Computable knowledge is a big push by Ultram. That could be a killer app for Exascale. Yeah.
And another, basically, going for this, also it very links to the previous question. I think making more real-time and fast decisions and data processing is maybe actually, commercial killer app for the Exascale. Now on Google and Facebook, everything is available, a few hours later. Now, if you can analyze, be it traffic, be it crime, be it whatever else, in real time, I think that's can be actually, very beneficial thing of what we can get out of Exascale on the very broad than just, climate simulations and stuff like that.
I think just a follow-on to that, I read it somewhere, I don't know whether you have seen, the supermarkets are trying to think, instead of a fixed price, they will determine the price based on the person who is walking there and based on his or her habit. So if that level, if they really want to understand your preference, how many units of that milk you are buying, at what rate, and how they can make a profit. They can change the price dynamically. I think it need not, this is depends on the supermarket and how many people go. That will be a big computing problem to do it in the real time.
Look, I've poked Mark a few times for fun here. The genius of what he said earlier about Exascale is that what you're really talking about is a new era of things. And we've got to stop talking about Exascale like it's an end point, right? It is an arbitrary milepost on a highway that is not ending. And in reality, there's nothing special about an exaflop that's more special than 967 petaflops or 1013 petaflops, right? It's just kind of a sign that you go by and you go, woohoo, we made it this far, and then you keep going. And that's the folly in describing what's the killer app for Exascale that's really going to be the one thing that makes it all worthwhile. The HPC market has never been like that, where, all right, tell me the 5 applications I need to dominate the space. In high-performance computing, the top 25 applications cover 40% of the market, right? And then there's a long tail below that. And this is the way it will continue to be, and we're going to continue to find new applications at the next road sign and the next road sign until we get to the end of science someday.
And if I can put one follow-up on this one, in your eyes, is the first exaflop machine is going to be actually cloud?
What do you mean the first exaflop machine will be in the cloud?
No, will be the cloud, will be a cloud, a large-scale cloud, not a traditional HPC system that we have in our mind today, but actually a large-scale cloud.
To build on that, that's a good question. So the question is, do you think that the first exaflop machine is going to be a heterogeneous base machine or a homogeneous base machine, or will it encompass cloud-based technologies as well as dedicated, I/O and compute resources? And that the implications beyond that are about all the software that supports it.
I can answer that one. So the way that I look at the cloud is that it's a delivery mechanism. It's a way that you interact with the supercomputer or compute resources. And typically in HPC we've logged in and submitted batch jobs and those kinds of things. It's a completely different usage model where you sit at your even phone or tablet or laptop or desktop submitting jobs through a browser interface to an infrastructure that you never log into directly, right? Beyond that, the delivery mechanism, there's a really hard choice to make, I think, for the cloud providers about how seriously they're going to take HPC, because what Amazon has done so far, what others, Microsoft has done so far, is that they've sort of continued to use the cloud interconnects of Ethernet and so forth, and that's great for a throughput workload, for a highly parallel asynchronous workload, but that doesn't characterize a lot. That characterizes some of HPC, but not all of HPC. And so to capture the rest of that HPC computing requirement into the cloud.
That makes that step up from Ethernet worthwhile in terms of cost performance and users.
I would submit that we've already created the first Exascale machine. Anybody who downloads holding at home on their iPhone or their mobile phone, and we have how many hundreds of millions of mobile phones. We may not be using that application yet, but they certainly could.
Intel traditionally has produced reference designs to both technologies, as I understand it. Do you have a reference design for the high-performance computer that you think will dominate in terms of architecture and componentry in 10 years' time?
No. Does it use Intel processors?
Yeah, Intel reference design uses Intel processors.
Almost uniquely.
Yeah. So we are definitely thinking about HPC from the systems perspective in partnership with our OEM partners. And there's a lot of integration that's taken place over the years. The memory controller came onto the processor, got rid of the front side bus. Recently, we've added PCIe to the processors, gotten most of the Southbridge, and so forth. And that trend will continue. The aggregation of more stuff on the processor, I think, will definitely continue. And the stuff that we're beginning to add has more impact on systems architecture. So we're thinking about systems architecture, but we also want to maintain a healthy HPC ecosystem of system providers and other technology providers that feed into that ecosystem. It's a very dynamic engine that creates innovation and value. We want to keep that piece of it. So we're in deep discussions with our OEM partners and other technology partners about how, as we integrate this stuff, they can still differentiate and create unique value proposition from their side. Now, there are a couple of other trends there that we see, pointing back at Google and Facebook and others, that we see, those guys are a big section of the server market, and their buying habits are shifting from buying systems and solutions to defining what those systems ought to look like and providing their own solutions, operating systems, networking protocols, all that kind of stuff themselves, right? And the value chain for the OEM partners is getting tougher to define, and that has nothing to do with what Intel's thinking about in terms of systems. It has everything to do with cost optimization that's going on in the data center space.
Let's move on to one that's been pitched in the meeting. So this kind of relates to a bunch of different questions that it's nice that we're talking about applications, because that can give you a little refresh perspective on the system. But When I first got exposed to modeling the aerodynamics of
hypersonic vehicles, and it's interesting how, I mean, just as one context, the thing with, when we go from petascale to exascale or whatever scale, I mean, from an applications perspective, it's really, I think there's two things that are become more interesting. One is you can solve bigger, more interconnected problems, right? Number two is you can do what ifs, right? And both of those are really powerful. But let's say if we look at, as a context, those two. And that doesn't mean for aerospace per se, because I think a lot of the exciting things in, in fluid dynamic modeling is being utilized in per patient tumor modeling for drug discovery. So, but the two things still come into like connected, or I guess you'd call it coupled multi-physics simulations. And the second is being able to do what ifs, right? But if you decompose that, and you look at how we solve those, right? You see a lot of reliance on adaptivity and unstructured methods in the numerics of these kinds of coupled multi-physics simulations, right? And if you look at that, and also if you're doing what ifs, that means whatever you're modeling, you want to represent it in a way where you can change aspects of the model and then resimulate. So this wreaks havoc on your memory system, right? So everybody knows this, but if you look across the industry, those systems are never really supported at any level, really. So if we look at if we look at from our programming models all the way down to the processor level, you guys mentioned that power and feeding the processor is really important. Well, if you have a dynamic time-varying graph that you have to walk that graph and do floating point computations on it, that's a problem. Right now, if we look at all the mechanisms, every major vendor across the board is doing a coherent shared cache. And we all know that doesn't help it, because you're always going to be blocked waiting for, in the innermost loop, you're chasing pointers down and you're waiting for random access to memory, right? So this is a quandary. And so what my real question is, when are we going to do something about that problem? Because if we address that, then a lot of exciting apps will be viable. And it doesn't matter if it's terascale, petascale, exascale, or whatever scale, because this is independent of all that.
Yeah, well, I couldn't agree with you more, and that's another area where HPC has a huge overlap with big data and data analytics and so forth, especially the big graph data analytics. So we have to address the memory wall, as I mentioned in my talk, and we're addressing the memory wall primarily from the perspective of, we got to move memory closer to the processor in order to, cut down the power that's required to transfer the data. I also talked about reorganizing the way the DRAM is set up so that when we go to read data, we only read the data you're going to use, as opposed to read a whole bunch of stuff that you filter out and send a small portion back. So yeah, we need a different memory hierarchy, and the needs in industry, the general big data market, fortunately line up with what we need in HPC. So I'm hopeful that over the long haul, those technologies will be developed. Now, to get to exascale by the end of the decade, for a machine that's 20 megawatts, I mean, those are very specific things that we need to accomplish to bring, the phase transition to science and stuff. That won't happen on that time scale with those kinds of results without, government sponsored R&D.
Yeah, I think I totally agree with that. And the issue is that, again, we have to build our systems out of the same building blocks that are available for general computing. Now, if you want to look to something a little bit more esoteric, like I think it's D-Wave, maybe that's a solution that addresses your particular issue. So when we look at exascale scientific computing, where you're talking about solving inner loops, maybe we need to have a completely radical technology applied, and quantum computing might be that technology. That's just my humble opinion, not a corporate opinion.
Okay, I have a separate question. This one's directed kind of at Bill Boas, because you have a talk tomorrow on the SKA telescope array project. certainly that has, it's like an Exascale system. Can you tell us how it's different, other than the fact that it's not tied to one government's tax base?
Well, the major difference is that when Mark talks about predictive simulation, in my mind, he's talking about data that's created in memory. Initial conditions are there, but then the application works on it and creates that further data in memory. And the I/O required for that is checkpoints and some final results. For the SKA program, the data is created in antennae that are capturing radio signals and is delivered over a network or networks to a series of machines that have to process the data as a unending, uninterrupted flow of data, right? Coming from the outside, and the purpose is to process it down from the rate at which it is received into a form of data that can be investigated by astronomers. That's a totally different kind of machine, right? And nearly all the conversation we've had here so far has been about flops and processors and memory. This kind of machine doesn't need flops, right? It uses memory as a temporary storage, right? And the computing is tens of thousands or hundreds of thousands of streams of data simultaneously arriving at the machine, right? And so it's a completely different architecture, and I don't believe that most of what we've known about in HPC over the last years really applies, right? It's different. And the commonality I see is actually with the commercial systems that we've been talking about. The supermarket, that's going to deliver data, and there are thousands of supermarkets around just this country who are generating data and feeding it in to machines that are processing it. And for me, that's actually a far more important market, not supermarkets, but the market for handling data, collecting it, receiving it, processing it, making sense out of it is a much more important market for society than predictive simulation of weather.
Yeah, start thinking NSA. They've already solved this one.
Any other questions from the audience?
I'll take another question. I think, Mark, when you talked about power, that was one element. If I take it to a broader way, there is a big issue of the cost of the system. And one way to reduce the cost of a system is to use the power scale, in meaning that if the same technology is going to be used in more and more places, you get a power scale, and things are going to become cheaper and cheaper. Now, I think it's a good thing that Web 2 applications or cloud application also going to the same kind of scale, because that's bring the power scale into things that needs to be built. Now, does that mean that the future it's going to be open source and standard based because it's going to be used in more and more places, and there is no more for proprietary anymore, or still there is a place for proprietary solutions? And it's a question for everyone, by the way. Not
Does it need to be more standards-based or proprietary?
Does the future does the future contain all just open source, standard-based solution, and no more place for proprietary technologies anymore?
No, I think there's an ongoing need for proprietary or performance-oriented solutions. And in fact, the need for that is getting greater as the standards run further down the commodity path. Now, you can make raw computing cheaper in various ways, but the further down that path you go, the more need there is for a higher performance technology to take on certain categories of harder problems. I think the economics for that are there. I think there's a straightforward business case even to say there's a market for systems that can do this kind of thing better than they can do that kind of thing.
Well, I think that innovation and all these things actually going up in the stock. And years ago there was a proprietary CPUs for the supercomputers. Now it's standard. A few years ago, there was a proprietary interconnects for the supercomputers. Now it's pretty much standard-based. And the innovation and the differentiation goes up on the stack. So I believe that all the infrastructure and foundation will be open source and standard-based. And on top of these platforms, people will, innovate and deliver the solutions.
Well, I mean, you make a good point, Michael, and here's where I could get proven wrong, right? Is that the investment model that we've been trained to recently is that people want to invest in the next big thing that's going to be really high volume. This is where VCs look. This is where people want to invest. These are the technologies companies want to invest in. I don't want something that has a $10 billion established market that's going to grow at 8% locked in. I want a 5% chance at $180 zillion, right? And if it's an established market that's got a proven growth rate, but it's not a market changer, forget it. I don't want to invest in it.
So let me disagree with you, Addison.
Oh, please, because I really wish that we could look at the HPC market and say, look, here's this $30 billion market that grows pretty steady around 7%. And, everyone goes, HPC, that's a tiny niche market. It's not worth investing in. Give me the next Angry Birds, which is a 1 in a million shot that you ever get to that. And you go, there's this whole market right here that's desperate for innovation that'll pay for it, right? But it's a mature market that's not $100 billion, so no one wants it. So prove me wrong. Go for it. I want that.
Well, first of all, not all of us are purely motivated by money.
When you begin to talk about applications level software, there's a lot of domain expertise that's very specialized that doesn't need to be transmitted to a computer center to run that infrastructure and is natural to be proprietary and actually packaged as an appliance, as a solution. And people will IBM figured this out and explained it to me when I was working back at Livermore, and it blew my socks off. Huh? Yeah, it's a different business model, right? If you have an HPC appliance, and you can go into an Exxon or Shell or somebody like that and say, look, you buy this appliance, it will cut your time to solution to getting oil out of the ground into the pump by 50%. That's a $50 billion impact to you. And this thing only costs you $300 million, right? When it cost me $50 million to build the hardware and the software to do that. You think they would pay that kind of markup from 50 to 300 to go from 300 to 50 billion? Absolutely. So the value proposition of software is the return on investment. And where we started this discussion on Exascale is, where's the Exascale killer Exascale app? And if we identify the killer Exascale app, that will drive the economic value proposition, that will spin us into a virtuous cycle of creating these new technologies.
All right. I did not mean to imply that open source software is or should be free. Nevertheless, if you go into end users in segments of the market that are dominated by ISV software, which predominantly happens in engineering-oriented fields like manufacturing, chemical engineering, etc., the prevailing viewpoints are that, 1, software is the limiting factor to my scalability, and 2, the software is too damn expensive. Right? And ultimately, the end users are looking to open source to being a hero space to providing more scalability at, not free, but a reasonable amount of money, where there's the perception that I'm handcuffed by these wicked ISVs who are out to make a profit.
Where did those ISVs get that software from originally? I think Mark knows better than I that an awful lot of it came out of the government labs, free to them initially, right? And the issue of the cost of software is maintaining and upgrading something that they originally obtained free, right? And those codes probably also run on top of MPI, which is free, and Open Fabric software, which is free. So the notion that software is damned expensive is actually very much in the interests of the business owners of ISVs, right? And limiting how much it scales is also in their business interest. It's not in the user's interest, but it's in their business interest.
No, I think, but how much it costs, it really depends between the person who sell it and the person who buy it. But the question started from open source and standard, and I think the open source and standard, regardless if it's free or not free, gives the ability of flexibility. An ability for someone to go and says, you know what, I can put an effort to optimize things to my usage. And that's kind of the strength of that. It doesn't mean standard and open source doesn't mean low performance. Right? If you look on everything that's being used today, Lustre is open source, right? And one of the most used storage options today. If you look on things that are being developed right now, for example, Ceph. It's not open source. That's something that can go there. It doesn't mean low performance. It means that it gives you the flexibility and it gives you a choice, which I think that's the strong part of things. I think Mark also mentioned the Slurm, right, for scheduling. That's open source. Probably maybe the most used one as well. So the question started from that point. If moving forward, the investment should be on standards and open sources rather than on proprietary elements because of that. But
I see it the debate between standard and proprietary. I think it is more like a pyramid shape. It will always be there. I'll take an example like cars. If you think of like cars over the last 20-30 years, a lot of technology which came to very high-end cars like BMWs and all, those technologies have gradually come down to very common car, and it has become like standard. So that similarly here you will see like in the HPC, some of the advanced technologies, there will be some market. People are ready to pay, as Mark said. Like there are companies, if you can distinguish, have some things, they will pay. But over the years that becomes very common, that becomes standard, and it comes as a standard, and it becomes like either open or an open standard, and everybody uses it. So I see it more like a pyramid kind of a structure, which will evolve over the years.
It was awesome, Mark, that you brought up the whole idea of about solving something specific for a particular target customer that it directly impacts their business case. I think that's total agreement there. But from that point of view, if you take that perspective, you can use open source in certain areas to interoperate with other things. But the problem is, if you're taking Mark's perspective and you're going straight ahead at that, and you're trying to solve a very high value, very business-oriented problem, then the problem with open source is it commoditizes things. There's a lot of influences that are going into that open source code base, thereby generalizing it so it fits on a number of architectures. Whereas if you're trying to solve Mark's problem, then you're going very specific, vertically integrated from the app all the way down to the chip. In that context, many of the implications of open source don't come into play. Not that you couldn't open source a new solution, that could come into play, but just leveraging things off the web and trying to connect them, because there's so many implications at the various layers up and down that it doesn't necessarily help you to address the larger problem.
Okay.
Right?
I think we could probably argue forever, but for simple example, how many here are using Linux and how many are using Windows for HPC? And Linux is open source, right? At the end of the day.
Elements inside of the Linux kernel, its communication to the user mode is so high, and there isn't a lot of talk going on in that. I mean, it's completely ignored. People don't talk about how much high latency you get when you communicate from the kernel mode to the user mode. And this stuff comes into play when you're solving a specific...
So the question where to fix it within Linux or to fix it as a proprietary element?
You can't fix it in Linux. It's the way the file system mapping works, and the way the Linux... Now, there might be ways of faking it, like the InfiniBand drivers is one way of faking it. But I'm just saying is if you're building a solution where memory access latency is the dominant thing, and you start to build on Linux, all the benefits you get at the hardware and system will go away at the system software layer.
So your view that in going to the Exascale side, it's not going to be Linux, it's going to be something else?
It has to be, otherwise you're going to... Now you might, I mean, it's possible because the InfiniBand drivers are doing some things, but just from my own personal experience, I would never build my app that I'm building on Linux. I would build it as a vertically integrated solution. Because at the end of the day, if you're providing a black box to the customer, why does it have to have Linux or any other technology? It just has to solve their business problem. And if solving the business problem involves, some set of technical decisions that percolate from the app all the way to the chip, what matters is, do they get their business problem at a factor of 30x improvement, like Mark was saying?
So I think actually, you mentioned InfiniBand, the intelligent hardware today enables you to run application on the bare metal, and all the operating system and other administrative tasks are being done sort of offline. So if you look at, you can run user-level sockets, you can run user-level file system, so there's no need to go from application to kernel.
If you're talking about doing communication from core to core and emulating message passing inside of that, you're stuck. And if you care about really low latency, especially in PDEs, differential equations, right? You care about not blocking your innermost kernel. So memory access latency in the innermost kernel for differential equation type solvers is more important than flops. That's where I'm saying is in certain cases it's dependent on the app. And all I'm saying is if you're building an app where the set of trade-offs in that particular app is really dominated, then why force fit it on any one open source layer? Solve the problem.
Right. So I think to solve this problem, if you look at the inter-node communication, then the problem is solved with the InfiniBand and alike. And CPU guys need to fix this problem within the core, within the socket, to make core-to-core communication to be as efficient as today we do inter-node communication. So there is no intrinsic reason why you have to go through OS. It's not some nature. It's just the way it's implemented today in the processors, and not that I have any specific idea how to fix it, but I think it can be fixed. And you do need to have administrative and resource management services that you don't want to do on your own for every machine or every application you are doing. What you need to do, you need to have these services not to stay on the way on the application.
I'm a combustion engineer working for automotive company. I'm very interested to hear that two topics that talk about today I did not expect to hear. The first one is on open source software. Currently at the manufacturing company like General Motors, that's a major issue, because as a manufacturing company, everything we do, including software, has to have proprietary. For example, OnStar system, everything is software. There are issues recently we have to deal with because for some reason, without clear check, we do have open source software in the OnStar system, and we have to get rid of it completely, redo the system. So open source software, it will carry with it with a lot of issue, particularly with the proprietary informations and with legal consequences with it. Currently, even within the company, we still don't know how to deal with that. So I don't know, this is a place to talk about it, but it's not just technical issue of implementing certain technology. There are a lot of realistic issues you have to deal with. The second comment is on Exascale. When 2 years ago, DOE come to Detroit and tell the auto industry leadership that the government is pushing for Exascale. You talk about peta, go to exa. They talk about 10 to the 6th factor of increase in computer speed. That's how they talk about it. So the people with a simple-minded calculation will say, yeah, now government is going to provide us with a computing system that can do our work 10 to the 6th factor faster. And that's all we're asking for, because we like to have a short turnaround of our design time for our product. Anything that can help us speed up our development process, we are welcome. We all love to hear it. But as we dig down to the reality, all the software we're using is non-scalable up to 100 CPU. Now you talk about exascale, and then the best you can do probably is run more job, not run faster jobs, right? Now run more job, great. That of course it helps, but it comes with another issue is, as a company like GM is global, everything has to dial into some system. If that is HPC, preferably probably is centralized. They come with a lot of security issues. Is that really manageable to be able to fully take advantage of running more jobs on the system? So this is just my 2 comments.
I'd like to ask the question, you said open source software creates legal issues. Would you describe what those legal issues are?
This is under legal review, I cannot comment.
I'm sorry.
Because by definition, if you go to open source, like OpenFOAM, you look at the term and the condition of the open source code. You have to be very careful reading the terms and conditions.
We still had 300 different, there's open source and then there's open source. In our product, we had to research every open source license that we include in our package. And we ended up with a license file of 300 different licenses. That's just a fact, that's just the way it is. And they're all slightly different. Some of them are very common, some of them are variations. I understand your pain.
That's exactly my point.
Yes.
So if you have an OnStar system with millions of codings, with millions of softwares in there, and you cannot screen millions of them and make sure all of them has a correct license.
Fortunately, I mean, yes, there are thousands of packages that we use. Many of them do copy the same GNU public license, for example. That is the same open source license for this package as for that package. But so many of them are slightly different or have other restrictions that in order to adhere to the open source license, in order to be able to include it in our product, we had to go through a great deal of legal gyrations to make sure that everybody is apprised, all of our OEMs, all of our end users, about the open source EULAs that came with our software package. So I do understand your pain. I wish open source people would, you know, let's just have one open source license.
Well, this is the challenge of it, right? Is that it is an open community that's going to go its own way sometimes. It's not going to be, I mean, if it were all rallied down onto one standard, it'd be like a proprietary solution. Just to add an industry perspective on it, that, you know, rather than dealing in the specifics, open source is not widely adopted from across all of HPC. Academia, research into biosciences certainly tend to be driven predominantly by open source. The engineering related areas tend to be dominantly 90+% third-party licensed ISV purchase software. If you go into certain other verticals like oil and gas, finance, you have a few important ISVs, but if you look at those too hard, you lose sight of the fact that the majority of the workflow is actually in-house applications and algorithms, and big data fits this same profile. The more you reach out into the high-performance business computing markets that I talked about before, the further you walk away from open source. I'm talking application software here, not necessarily operating systems. Open source application software being the dominant paradigm. Now you're going to ask me about operating systems next. If you go into commercial markets, Windows, Linux wind up being, well, it's still Linux dominantly in HPC areas, but then you get outside of that into the rest of the enterprise, and there's a lot of windows. And big data, which we're talking about is being a driver for Exascale in the commercial space, has as much Windows as it does Linux right now. It's about even in our big data studies if you go into the non-HPC commercial environment. So, we're talking about trying to get people onto things like Lustre. They're not on NFS now, they're on CIFS. Right? And you're trying to get a scalable parallel file system. So, the discussion about open source is relevant, but you have to realize how many steps removed you are from a lot of the volume of the market that we're talking about.
So I'll just tell you that Oracle Exadata uses Open Fabric software, EMC uses it, NetApp uses it, all the major stock exchanges in the world run on it. Right? And it's open source, it's in Linux, and it's in Windows.
You're talking about the specifics again, where I can name 4 really scalable ones that do. I'm talking about the volume of the market that is in these vertical market categories does not. And then I'll amplify the point by saying, go back to my presentation, I'm talking about the shift in skill sets that's required. If you start walking out from ISV software into open source software, you're again talking about introducing a skill set into your organization that you might not already have in terms of managing what versions of open source things we have. It's a different kind of administration you might not be doing currently.
So I was just mentioning where this particular piece of open source is used widely throughout the world in big data, in industry, right? And
I think that's super.
And the legal issues associated with it, I have been involved with this organization for some time that produces this, and probably the biggest surprise in 10 years I got was bringing Microsoft into this organization, and there was not one question about licensing or patents or any legal issue around Microsoft using this software. Right? So the idea that open source produces legal issues of a legal type as opposed to a range of different licenses, which I understand, right, is not necessarily the case. And it's all in how the open source, the people who are developing the open source and who have the copyright to it choose to license the software.
It's a really fair point, Bill. It is, and I get it. When legal issues come up with respect to licensing, with respect to big data, with respect to cloud and security, oftentimes the legal issue is a substitute for phobia, right? And it's kind of like fear of flying. And I can say, I have this fear of getting on this jet because it's going to crash. And here's examples of plane crashes. You can answer me with a raft of statistics about how safe flying is and why I shouldn't be scared. And it doesn't answer my phobia and my desire to go back and say, but this one crashed. And you get this with legal issues sometimes where the legal or security issues come up, and I wonder how much it's just an organizational hesitance to do something because I'm conservative.
So I just want to cut this because we have 2 minutes to end, and it's becoming an open source panel. So I think we talked enough about that. And talking about plane crashes, I have a flight on Wednesday, so let's cover plane crashes. Yes. So last question that I wanted to ask, and the reason I want to ask it because I want to connect it to tomorrow, and invite you all to come tomorrow as well and to hear also first I think very interesting keynotes, but there is also a session that IBM is going to talk about open power. Now, Addison, you talked about IBM selling the x86 to Lenovo. And what does it mean from the Lenovo perspective? The things on the IBM side, that means that one of the biggest HPC companies is going to push power into HPC. So now we're seeing power, and we're seeing open power, which is an initiative that includes IBM and Google and NVIDIA and Mellanox together. We see ARM coming, right? And ARM is coming from the same point that x86 came, from the low end. It's trying to come into the data center. So I think we're getting into a very interesting era, which not going to happen, next year, but in the next 2-3 years, you're going to see power as an alternative, ARM as an alternative, and x86 what's the view here about, x86 is going to continue to be a dominant factor, or we're seeing a very serious competition from power, driven by Open Power and IBM and ARM?
I'll back the cleanup on this one.
I'll just start by restating the industry context that, we try to keep our finger on the pulse of this thing in the end user community as best we can. I can't think of a previous time in HPC when so many different competing processing architectures were simultaneously an active part of the conversation. That's essentially what we're dealing with here. And the end user community is reacting thus far by going, I don't know, we're going to test them all. We're going to try to see where we're going. It's very early days right now to predict how this is going to evolve. What we can do is predict how should we be asking the question, or how should these evaluations be done.
I'll just say that we're definitely researching other processors besides Intel platforms. We're currently Intel based, but we're definitely looking at other ones.
Some time ago, I think it was Mark who talked about cell phones and tablets, and associated with them, I think most of us think ARM these days. And then we think that there's x86 and there's ARM and that's it. Well, Gilad has mentioned power. There's actually a marketplace that we're ignoring, which is the commonly known as the network marketplace. But that marketplace is actually growing and being driven by the cell phone and the tablet use. And the infrastructure that we all use when we get on our devices is a network infrastructure from the tower through the physical network infrastructure to the data center. And the appliances in the front of the data center for processing what we do. That marketplace is predominantly a power marketplace. It's growing very fast, and the performance requirements driven by all of our behaviors are extreme. There's chipsets available today, many of them based on power, that have throughput that is at least equivalent to x86, if not better, have I/O infrastructures for multiple different types of I/O, as in Ethernet or rapid I/O or various forms of Ethernet. There's a chipset on the marketplace today that offers 4 40 gigabit Ethernet connections on chip. And behind those connections are accelerators on chip that allow you to move data in and out of the chip without going to the processor and without going to memory. This, I believe, is the kind of architecture that is, if we were aware of it, we would be looking at very, very seriously. And the dominant instruction set architecture for those chips is power.
Well, you touched an interesting point that actually network value and network contribution is getting higher, and obviously I agree with this. In terms of the microprocessor architecture, I don't have any strong affinity to either one of them, despite working for Intel for about 16 years. But other than that, you actually seconded that there's multiple players coming to the CPU space, and the future will tell how it does evolve. I wouldn't take a shot predicting something.
Okay, so I said I'd clean up here. It's a very the strength of the IA ecosystem is enormous, and its penetration into HPC has been extremely remarkable. One of the founding tenets of that, I think, is the quality of Linux on IA, which Intel is, just trades with Red Hat as the #1 contributor to the Linux kernel. That didn't happen, overnight. That happened over a long period of time. And experimenting with other architectures, I think, is a place where innovation happens, and we see that innovation, and we're tracking that and trying to compete with that and innovate in that environment as quickly as those other processor architectures. One of the things that we're doing to compete in that area is integrating system-on-a-chip design methodologies top to bottom, and starting with the bottom and going up. And so that's a phase transition that's rippling through our design methodology right now that will be a fundamental shift. The other thing that system-on-a-chip design methodology allows you to do is variance very quickly. You don't have to, and by changing IP blocks within an SoC design methodology, you can create what we call SKUs, products that target specific markets like networking, much more rapidly than you could with the monolithic design processes of the past. So we are definitely interested and focused on competing in those marketplaces. And in the killer micro revolution, when we moved off of mainframes and it was the killer micros that sort of remained standing there was a lot of architectural innovation. IA was one of many coming out of that revolution. And that architectural war, there was a lot of consolidation down to a few architectures. Now, because of phone and tablet and system-on-a-chip design methodologies for these emerging markets like networking and HPC, that innovation is coming back in another wave, right? But where that wave, lands is, I think, one of the challenges that we have at Intel and are very aware of it and going after it.
Just one more comment. You mentioned system on a chip, and I think it's an interesting point because the way you look at the system on a chip is basically addressing the packaging, which as a packaging which is can address power and performance, but in terms of ecosystem, I think you are more choking than developing it. Because if you would follow our model where you can let people do their system on a chip with your core, then it will develop ecosystem. Otherwise, I think it's pretty much choking it.
Okay, I think with that we're kind of 7 minutes after time. So I want to thank all the panel members, Mark, Ellen, Bill, DK, and Michael. Thank you very much.